Now that we know there are so many galaxies, 100 billion plus in our universe, what are the chances of them interacting with each other? Well, it's pretty high. The galaxies don't evolve alone by themselves. So the way in which they interact with each other is an important part of the history of their own development. The galaxies are close enough so collisions really are inevitable, as opposed to stars. If we look at the scale of the galaxies, typical size galaxies here, this would be the average distance between them. So somewhere on the order of 1 or 2 magnitudes of distance compared to their scale. That's a lot different than the stars. Star collisions are very unlikely. Why? Because if I had a star, if you could visualize my words now, about the size of a tennis ball, if we scaled it down to that, the next star distance on the average in a galaxy would be about 1,000 miles away. So I don't know how far these are spread out on your screen, maybe a foot or so apart depending on what you're looking at them with, but many orders of magnitude difference in the relative spacing between the stars and the galaxies. So stars, no collisions. Galaxies, yes. Here's an example. NGC 4038 and 39. Two galaxies merging with each other. You can see the tidal tails that are being spread out here as a result of this merger. And vast regions of starburst, incredible starburst activity going on as a result of all this gas shock taking place. The nuclei of these two galaxies will eventually come together. They've already passed through each other in this particular case. So that was a good setup for an observation we make in certain galaxies of incredible starbirth, star formation. We call them Starburst Galaxies. It's really a stage in a galaxy that we discover where this is happening, where the star formation rate is unsustainable. Here we see two bright spots corresponding to the bulges of two galaxies that are coming together. The spectrum here in this graph shows the amount of infrared radiation which is a part of the total luminosity of the galaxy. And it's very prominent with respect to the rest of the luminosity of the galaxy. So a starburst galaxy is one where it's producing stars at a rate of about 100 times the normal production rate. Now at that rate, you cannot sustain the ongoing star formation because it'll use up the dust and gas relatively quickly. So this is unsustainable. In this example here, with this graph, we have a galaxy that is about as bright as the Milky Way galaxy in visible, but about 100 times brighter in the infrared. So it's evidence that there is huge young star production that's heating up the gas that's associated with the galaxy and producing tons of infrared radiation. Well, copious amounts of infrared radiation. And the common theme is what we just covered prior to this, where it seems like these are associated with merger events between galaxies. The Starburst galaxies have particular emission characteristics revealing different aspects of what is going on. Very rapid star formation can result in actually producing galactic winds, literally on a galactic scale, that are so strong they interact with the surrounding gas, producing X-rays as outflows from the galaxy. So here we have visible light, image of violently disturbed gas. And here is that same region in the X-ray. So we can see that there are very energetic processes going on. The bright dots are X-ray accretion disks from neutron stars, black hole, binaries, that type of thing. Here is NGC 1569. There's a supernova production rate that's so extreme it's driving out the gas out of the galaxy. So supernova can actually produce these galactic winds that can push the gas or clear out of the galaxy, strip the galaxy of its gas, which will subsequently inhibit star formation because the raw materials are no longer available to produce the stars. So in this way, heavy element production is brought to a stop. The hot massive stars die out in a few hundred years, just kind of 100 million years, and they act more like ellipticals at that point. So this is an emerging arena of understanding of starburst galaxies, and with our high-tech ability to image the processes going on, we're seeing in more detail how these galaxies are evolving very uniquely. Here again is the merging galaxies we saw before. It's the antenna galaxies, and you can see the antenna structure, the tidal tails being extended out here with the two nuclei of the galaxies. Incredible process taking place in real time here. Very slow motion. Here's a bunch of examples of merging and colliding galaxies. Star collisions, again, unlikely. Galaxy collisions, likely, producing tidal tails, triggering star formation. And they may account for the emergence of ellipticals in some cases. The merging mice galaxies. You can see the huge tidal effects going on as they pass through each other, stretching each other out. If we could only take an image every 10,000 years or so and then play it back at a high rate of speed so we can see it, this whole thing occur in real time in about a minute or so, that actually takes hundreds of millions of years for the collision to actually occur. Here's another example in Virgo. Here's a collision in process. It almost looks fake. These are two grand design spirals that are coming together as we speak. And one more time, this very high resolution, very well studied merging of these two galaxies. There's the cores of the galaxy. They've already passed through each other, but just look at the unbelievable amount of stellar activity going on from the shocked gas clouds, producing tremendous quantities of new stars, OB associations, supernovas, all kinds of interesting stuff going on with this incredibly violent collision.
The Hubble Space Telescope has produced a close-up view of the galaxy Centaurus A. Hubble's multi-wavelength image is the most detailed ever made of this dynamic and dusty galaxy.
Centaurus A is well known for its huge dust lanes that stretch across the entire extent of the galaxy. Now, Hubble's new observations are an extreme close-up of a small part of these dust lanes. This new image is made from observations in ultraviolet, optical and near-infrared light. The ultraviolet light shows us the locations of hot young stars, whereas the near-infrared light allows us to glimpse some of the details that are obscured by dust in the optical.
Astronomers think that Centaurus A must have collided and merged with another galaxy at some point in the past. The shockwaves of this event caused hydrogen gas to coalesce and sparked intense areas of star formation, as seen in the red patches visible here. The turmoil of this collision also explains the warped shape of the galaxy's disk.
Looking at a broader view, taken by ESO's wide-field imager, reveals the extent of the distortion in Cena's shape, as well as further areas of vigorous star formation.
The galaxy contains a highly active supermassive black hole at its centre. Powerful relativistic jets release vast amounts of radio and X-ray radiation. Although Hubble can't see this, submillimeter telescopes like APEX can see broad plumes of matter being ejected far out from the galaxy.
At a distance of just over 11 million light-years, Cen A is relatively close in astronomical terms. In fact, it's not only close, it's also very bright. Amateur astronomers with a view of the southern skies can actually see it with just a pair of binoculars, while those with a largish amateur telescope can even make out the dust lanes.
But only Hubble reveals this much detail. Not only does the Space Telescope offer unprecedented clarity due to its position above the distorting effects of the atmosphere, it is also able to observe ultraviolet and infrared wavelengths with pristine clarity.
So galaxy emerging and collision events are most common in rich galaxy clusters. Collisions are relatively common there, but perhaps not ones like this amazing image shows. Several galaxies coming together all at once. So that's pretty awesome. Future prognosis for that set of galaxies. But in addition to these merger events, which are associated in general with relatively equal-sized galaxies, we also have bully galaxies, which are massive galaxies that consume all the small galaxies around them. Well, not necessarily all of them, but they tend to chomp up the small dwarf galaxies like hors d'oeuvres. And these have no set limit in terms of how big they can get. They're the most massive galaxies in the universe, and they're always ellipticals.